Hello everyone. Today let's solve the problem number 787, cheapest flights within K stops. So what the question states here, we are given n cities, means number of nodes here. You can just consider uh, the cities as nodes here. We are given n cities and list of flights represented as from, to and price. So a list of flights they have given here. This will be from, this will be to, and this will be price. So we are given n cities and list of flights represented as from, to and price. Our main goal is to find the cheapest cost to travel from source to destination. So what is our main goal here? To find the cheapest cost to travel from source to destination with at most k stops. Here k is nothing but how many stops, number of stops here, and we have to find the cheapest cost to travel from source to destination with this one, with at most k stops. If no valid route exists, then we have to return -1, right? So just keep this one in mind. If no valid route exists, then we have to return -1. So let's come to the example 1 here. We are considering example 1, right? So here this is nothing but from, to and price they have given here. So this is accordingly with the diagram they have given right here, 0, 1, 2 and 3. Here you can clearly see. In source they have given 0, destination they have given 3. Means we have to move from this one 0 to 3. We have to find the minimum cost it takes to travel from 0 to 3. Nothing but here source 0, destination 3 they have given. K equals 1 they have mentioned. K equals 1 means here we can have one stop, right? So one stop they have mentioned here. So the output they have given 700 here. You can clearly see. So how we got 700 here? You can clearly see here. This is a directed graph. They have correctly shown here. You can see the arrow mark. This is directed graph, right? So we have to travel from 0 to 1, 1 to 3. So here, as this is directed graph, we have to travel from here. We have the price is 100, 0 to 1. Then we have to travel from 1 to 3 this side. So the price is 600. So 100 plus 600 is nothing but 700. 100 plus 600 is 700. So the output that they have given here is 700 for the first example. So same goes with the second example and third example as well, right? You can just go through second and third example. In the explanation they have given here, the graph is shown above, the optimal path with at most one steps. So we have to consider one step. This is this one stop, right? So this is one stop, and then we can just go here 1 to 3. So in this case, the optimal path with at most one stop from city 0 to 3 is marked in red. You can clearly see here, nothing but 100 plus 600 here, 700 marked in red and has a cost of 100 plus 600, 700. Note that the path through cities 0, 1, 2, 3 is cheaper but is invalid because it uses 2 stops. So it is saying it will use 2 stops. So this one they are considering. 0 to 1 we have 100, and 0 again 1 to 2 we have 100, and 2 to 3 we have 200. So overall we have 200 plus 100 plus 100 is nothing but 400 here. But they have asked us to find with one stop. K equals 1 they have given. So here we have 2 stops, right? So just give me a second here. In this case, this is one stop and this will be another stop. The final one will be this one, right? So 100 plus 100, 200, 200 plus 200, 400. So we got the minimum value, but stops we got is 2. So this fails actually, right? So we will consider this one, this path, 100 plus 600 with one stop, nothing but 700 will be the output. I hope the question is completely clear. So let's discuss the approach. I'll just consider the same example, example 1 for the approach. Let's discuss the approach followed by edge cases one by one, and then finally write the code and discuss the complexities of the code that we have written. Initially, let's discuss the approach. Here, you can clearly see we are going with I have just considered the same first example, right? So what we need to find here, we need to find the this one, cheapest cost to travel from source to destination. Source from 0 to 3. The same example, first example, from here to here, 0 to 3 we need to consider. Edges can be from anywhere, but we have to consider only one stop. So we can move from any path. This is just I have showed that we have to travel from 0 to 3, from source to destination. Source they have given 0 and destination they have given 3. K is nothing but the stops. So one thing we have to keep in mind here is we will be making use of Bellman-Ford algorithm. So just keep this in mind. We'll be making use of the Bellman-Ford algorithm. So if you don't know Bellman-Ford algorithm, please to go through the playlist. I have the playlist mentioned important algorithm. So I have been explained about Bellman-Ford algorithm, Dijistra's, so topological sorting. Most of the important algorithms I have explained there. So you can just go through that one and you can come back so that you will understand the concept clearly when I say something, right? So next, let's move on with the step 1 here. So first step, first thing we are going with the Bellman-Ford algorithm. We know this one, right? So what will be the first step here? We already have the graph. So we must find the cheapest cost from 0 to 3, at most one stop. We know that. First step here is initialization of the costs. Initially what we will do, we'll go with 0, initializing the cost with infinity as well as the infinity here. Cost of 0 will be 0 initially. This one, cost of 0 will be 0 because we have SRC, source 0. Source itself is 0 initially. So cost of 0 initially will be 0. I hope this is clear. So this is initializing the costs, right? So this is the first step. So let's move on with the second step. Just give me a second here. So here let's move on with the second step, nothing but iteration 1. When k equals 0 means 0 stops. When we are considering when we are having 0 stops means when k equals 0, k equals 1 means we have to go with one stop. When k equals 0 means we don't have any stop here. Initially what we will do, we will consider temporary variable here. Temp equals initially 0, infinity and infinity. This we know from the initialization of the costs, right? So it will be 0, infinity, infinity and infinity. Let's process the each flight here. 0, 100 we have. This will be basically temp of 1. Temp of 1 we are considering right now. Temp of 1, this will be 0 plus 100. Nothing but in this case it will be 100, right? So second one, 1 to 100. So these are all the things that we need to process in the input they have given here. So here you can clearly see 0, 100. So 1 to 100, this one. We need to process this one step by step, right? So here this one will be 100 because k equals 0 we are considering. So temp of 1 will be 0 plus 100. This will be 100 for this. 1 to 100, this will not be updated. So this will not be updated. Why this is not updated here? Because we know that cost of 1 is still infinity. Cost of 1 is still infinity. We know that one here. You can clearly see cost of 1 is still infinity. So this will not get updated here. So I hope this is clear. These are also not updated because we have infinity and infinity. You can clearly see here this one, this one. So let me give here let me give here not updated instead, right? This will be not updated as well. So this one will be temp of 1, whatever we have written here. This will be 100 basically, first one, right? So updated cost, let me write here, cost here equals initially 0. Cost of 1 will be now 100 as we got 100 and other two will be infinity itself. So I'll just give here infinity and infinity. I hope this is clear. This is updated cost array. I hope this is completely clear. Next, let's come to the step 3. Nothing but iteration 2 here. We will create this one, temp this one temp array where 0, now we have 100 in this place, cost of 1, infinity and infinity. This will be there. So let's process each flights now. We have 1 200 and 1 3 600 here in this case. So this will be temp 2. So temp of 2, and this will be temp of 3. So temp of 2 will be here. We have 100 here. 100 plus 100, we are considering this one. 100 plus 100, this will be 200. This is fine, I think. So next here 100, this one we are considering 100 plus 600, we have 600. This is 700. So I hope this is clear. Sorry, just give me a second here. So yeah, this will be 700 basically. Now temp 2 and temp 3. So temp 0 we have this one 0. Temp 1 we have 100. Temp 2 we have, temp 0 is 0. Temp 1 is 100. Temp 2 is 200. And temp 3 is 700 we have, right? So we can write in this way. Now temp 0 is 0. Temp 1 in the previous step we had 100. Temp 1, temp 2, sorry, is 200. And temp 3 here is 700. So I hope this is clear, right? So the final cost array here would be, I can consider here cost equals temp 1 0, temp 2 100, temp 3 200, and temp 4 finally 700, right? So the cheapest cost from 0 to 3 here is 0 1 2 3. The cheapest cost from 0 to 3 here would be 700, the last one, right? With one stop we have is 700 here, right? So I'll just give here, in this case the output will be 700. The cheapest cost from 0 to 3 with at most one stop is 700. So I hope this is clear. This is the approach that we will be going with. So we have made use of the Bellman-Ford algorithm here, right? Modified Bellman-Ford algorithm. So I hope the approach is completely clear. Next, let's discuss the edge cases step by step. First edge case that I'll be considering here is no valid path. So here n equals 3, flights they have given 1 0. So source 0, destination 2, and k equals 1. If we can visualize in the same way that we had discussed for the first example for the approach, right? So output will be here -1. Why the output here is -1? Here no route from 0 to 2. So we have to go from 0 to 2, right? So no route from 0 to 2. So I'll just give here no route from 0 to 2. So the output will be in this case -1. So let's move on with the second edge case. Second edge case, we are considering direct flight available. So direct flight available, again clearly see from 0 to 2. You can just draw the graph and you can just visualize in the same way that I had shown for the example one. Again I'm saying, so here direct flight is used, so output will be in this case 500, right? So this is for the condition direct flight available. We have made use of the direct flight, so the output will be 500 in this case. So the third edge case is for more stops but not allowed. We have more stops here, k equals 1, but it is not allowed at all because we have to move from source 0 to destination 3 here. In this case, you can just draw the graph and you can just see in this case output will be -1 as well because it requires 2 stops at any cost. If you draw this one graph for this one, we will come to know that it requires at least 2 stops, right? But k we have here 1. But here we need to go with the more stops, but it is not allowed in this case, right? So the output that we will display in that case, we need more stops, but it is not allowed here. K equals 1 they have given in for the edge case that we have considered. So output will be -1. I hope all the edge cases are clear here. The first edge case that we went with here is no valid path. The second edge case that we went with here is direct freight available. The third edge case that we went with here is more stops but not allowed. I hope all the edge cases are clear along with the approach that we discussed. Next, let's start writing the code. So let's start writing the code. Initially what we will do, let's initialize an array cost with the infinity values. So I say I'll just go with the cost and let's initialize this one cost. And let's initialize an array cost with the infinity values. I'll just consider here new array, array of n. Let's fill this one with infinity. So this we got from the idea from the approach itself, right? This we have to get the idea from the approach itself. First thing is the source city has 0 cost, right? We have discussed about this. The source city has 0 cost initially. So cost of SRC initially let's give here 0. I hope this is clear. The second step is we have to iterate k plus 1 times to allow k stops, right? We have to iterate k plus 1 times to allow k stops. So I can write in this way. So while k minus minus decrement k, this is greater than or equal to 0. So why it has to be greater than or equal to 0? Because we have to iterate k plus 1 times to allow k stops, right? So let's create a temporary copy of the this one cost array. So we are going with the temporary copy. If you remember the approach, so we are going with the temp, right? We went with the temp, if you remember. So let's create a temporary copy of the cost array. So I'll just give here, let temp equals spread operator of this one cost. I hope this is clear. Next step is we have to relax all the adjustments. We let's go with the Bellman-Ford style, or let's go with the Bellman-Ford algo here. So here let me give for let dp. This is fine of flights here from to and the price, right? So we are just going with the Bellman-Ford algo or style. So if the source city has been visited already, if the source city has been visited already, and if it is not infinity, in the step 2 we came to know that in the step 2 the final cost array was 100 for the source city. From it was 0 initially, the source city, and in the next step it was 100, then it was 200, then it was 700, right? So step by step. Though, so if the source city has been visited, not infinity, and the cost to the destination is cheaper, then we have to update it. Simple if condition here. I'll just give here if cost of S here less than infinity and temp of D. D we have considered here, right? SDP from to price. So here temp of D greater than cost of S, then plus P. P is nothing but the price. So here this one, what we have to do, then we have to update it. Updation is nothing but temp of D equal cost of S plus P. So I hope this is clear. What we are doing here, if the source city has been visited and if it is not infinity and the cost to the destination is cheaper, so then we have to update it, right? So that's what we have done here. So the last step here is we have to update the cost array with the new values, right? So here we have temp, we have considered temp as this one cost. So here what we are doing, we are updating the cost array with the new values. So cost, let's initialize this one to temp, right? Let's assign this one to temp, sorry, not initialize. So the final step here is let's return the final cost if reachable. So we have to return the final cost if we can reach from source to destination within the k stops that they have mentioned. Otherwise, if it is not reachable, then we have to this one, return -1, right? Let's return the final cost if reachable. Otherwise, let's return -1. How can we write that? I'll make use of the ternary operator here. So this will be cost of DST, destination they have given here. DST is less than infinity. Then what we will do? We will return cost of destination. If not, then if it is unreachable, then if it is not reachable, then we can just return -1 in this case. So I hope this is clear. Let me format this one once. Let me hit the run button. I hope this works. Let's see. We have a runtime error here. Constant identifier src has already been declared. So why did I give here const? So this has to be cost, not const, right? So they are initializing cost of src equals 0 initially. So what we are doing here, the source city initially has the 0 cost. So this has to be cost, not the const. So let me hit the run button again. Again, I have given const everywhere. The line number 14. Oh yeah, I have typed const, I think. Here also let me change this one again. Const, cost, it has to be. So now you can clearly see the sample test cases are getting passed. So let me hit the submit button. I hope this works. Let's see. So you can clearly see here now all the test cases are getting passed, right? So let's quickly discuss the complexities of the code that we have written. So the approach that we went with here is Bellman-Ford algorithm. We know that one, right? So we went with Bellman-Ford algorithm. So what would be the overall time complexity here? The overall time complexity here would be big O of m into n, or we can just consider n into m or m into n. So what is n here? N is nothing but nodes, number of nodes or number of cities. Here we have considered cities as nodes, right? N is nothing but the cities. M is nothing but flights up to k plus 1 iterations. We saw this one up to k plus 1 iterations. When I said we saw the we considered first example that was given in the question in the approach. So in the approach we saw the same thing, right? So I have explained that one clearly. N is nothing but cities, M is nothing but flights up to k plus 1 iterations. So overall time complexity would be here big O of n into m. So what would be the space complexity here? The space complexity here would be overall space complexity would be big O of n. Why it is big O of n here? Because we have only two arrays. One is cost and another one is temp. You can clearly see here cost here and the temp here, this one. We have two arrays. One is cost and one is temp. So overall space complexity here would be big O of n. I hope the solution. So just give me a second here. Yeah, overall time complexity would be big O of n into m, and overall space complexity would be big O of n. I hope the solution is completely clear. For now, this is it. Thanks for watching, guys.